Okay, so today we are gonna discuss some atomic arrangement and structure of metals. Basically, okay, we're gonna focus on metals, and their structures are like FCC, the phase center, BCC, body center, and CP, crystal structure. We're gonna introduce this in detail later. And those atomic arrangement, those atomic arrangements are highly influences its mechanical behavior and mechanical properties. Okay, therefore we have to uh, realize its crystal structure, how to evaluate, how to calculate, how to define its crystal structure, how to define, okay, how to identify its crystal structure. Okay, also we have to identify the close packed plane direction. The reason why are the cross-pack planes and directions are highly, uh, you know, it's highly related to its mechanical behavior and properties. For example, if you apply a tensile stress on a metal rod, for example, for aluminum rod, we just apply the force to put it to fail. Finally, you figure out the fracture plan. The fracture plan is not smooth. It must be along some crystal plan or direction. Okay, and that's crystal path plan. Okay, therefore we have to find a indices to define, to identify the crystalline plan and direction. It's called the Miller indices. Okay, it's called the Miller indices. I will introduce this later. Okay, and the issues to address are how do those how do atoms assemble into solid structure? As I already mentioned that the FCC or BCC or HCP and so on. And how does the density of materials depend on its structure? Of course, if if there are the highest number of atoms in unit volume, of course, it must have the higher density than that of others, right? And what do materials property vary with simple orientation? Okay, that's the isotropic or anisotropic. Okay, the materials isotropic or anisotropic. That is the materials property, whether the material properties depend on its crystalline orientation. Okay, so for atomic arrangement, first is called the no odor, like the monatomic gas, okay, like argon, okay, or it's amorphous, okay, materials is without any periodic fashion, okay, without any periodic fashion, and its molecule or atoms are randomly moving. Okay, we can call it amorphous. Okay, and I'm sorry. And the second structure can define as a short range odor, SRO, if odor extended only to nearest neighbor particles. Could be atoms or ions, like water molecule. It's a hydrogen bond between the oxygen and the hydrogen. Okay. Okay. And the long range odor, LRO, materials with a crystal structure fell in the LRO category, and crystal materials might consist of either single crystal or polycrystal Okay, polycrystal. I will introduce this later. Okay, and for the polycrystal, many misaligned crystals are called grains. Grains. Okay, and the grain size and grain boundaries are highly related to the mechanical properties. Okay, mechanical property. Okay, here the first figure A shows the argon gas, right? It's a monatomic gas, so it will move randomly. So it's amorphous. Okay, it's an inert gas, no odor. Okay, or amorphous. Okay, and for the B, it's water. Okay, water. It's only exists the odor only existing between the hydrogen and the oxygen. And for the water molecule, it's randomly moving. Okay, it's randomly moving. Okay, so usually we'll define the water structures is amorphous. Okay, amorphous. Okay, and for C, figure C, it's silica. Okay, silica. Okay, silica. Basically, it is ordering between two nearest neighboring atoms. Okay, but for the whole structure, it's still randomly arrangement. Okay, random arrangement. And for the figure D shows the long-range odor structure. Basically, the unit cell, the single. I will introduce this later. A smallest repeating unit can be extended, okay, to form a 3D structure. Okay, it has the periodic fashion to form a 3D crystalline structure. Therefore, it is the long-range odor structure. And metals, alloys, many ceramics, and some polymers, okay, has the regular odoring of atom or ionic, okay, that extends through the material. Okay, so for most of the metals are polycrystal. For example, like the sphere shows stainless steel. It shows the stainless steel. It's polycrystal, and this is the grain size like this. The misaligned crystal to form the grain, right? Is the grain, and here is the grain boundary. Okay, grain boundary. So you can imagine that the grain size and grain boundary is a must. Now we are highly emphasizes its mechanical behavior, right? Okay, the large grain or smaller grain, or the higher density of the grain boundary, basically will vary its mechanical strengths. Okay, mechanical strengths. And there's a special materials called a liquid crystal. I think it's quite common use, right, in our daily life, like LCD, liquid crystal display. Basically, it's a rod-like structure. Okay, it's a rod-like structure. Okay, and it's polymer. Okay, it's rod-like structure, and we have two electrode, transparent electrode. Okay, and when we apply a voltage, okay, it's called the external stimuli. It's right, like external voltage, external potential, or external temperature. Therefore, as we apply external potential, this rod-like structure will rotate it. Okay, we will rotate it like this. We will rotate it. Okay, therefore it can be used in the display or monitoring industry. Okay, and next we're gonna tell you how to define a crystal structure. Right, we always say, oh, it's crystalline structure. It's crystalline. It's polycrystalline. It's amorphous. It's short range order, and so on. Therefore, we have to define a crystal structure. Okay, crystal structure. Therefore, the crystal structure can be defined by, can be defined by the lattice and the basis. Okay, and lattice is a collection of point arranged in a periodic pattern. Okay, such that each lattice point's surroundings are identical. And a basis is a group of one or more atoms arranged in a particular way with respect to each other and associated with each lattice point. Okay, what does this mean? For example, here it's a one-dimensional structure. Okay, for A, it's a one-dimensional lattice with lattice point right here. Okay, with lattice point. Okay, and for B, it's the basis. It could be one atom or more atom. Okay, and for the C is we put the basis in each lattice point. Okay, lattice point. It's okay. So for C, it is a crystal structure. For C, it's a crystal structure, one-dimensional crystal structure. And also, we can replace one atom to two or more atoms. Okay, and it can shift. Okay, it can shift. This basis can shift to different lattice point. Okay, the different lattice point. Okay. Okay, in 3D structure, there are 14 unique ways to arrange points in 3D space. Okay, they are called the Bravais lattice. 14 unique way. Okay, 14 unique way. 14 unique way with three structure system. Seven structure. Seven structure system. One is a cubic, tetragonal, hexagonal, and the monoclinic, rhombohedral, and orthorhombic, and so on. So, there's still one is called triclinic. Okay, therefore there are seven system, seven crystal system. Okay. Okay, there are seven crystal systems right here, and the 14 Bravais lattice. Okay. And unicell. Unicell is a subdivision of the lattice that still captures the overall lattice characteristics. Okay, and the atomic order in crystal solids indicates that the small group of atoms form repetitive patterns. Thus, in describing crystal structures, it is often convenient to subdivide the structure into small repeat entities called the unicell. Okay, therefore, the small group of atoms can be regarded as the unicell. That is the repetitive pattern. Okay, repetitive pattern. For example, the figure A shows a two-dimensional crystal. Okay, two-dimensional crystal. Okay, and we have a single unique cell. We have a single unique cell. I'm sorry, single, like this, single unit cell. Okay, and this unique cell can extend through the materials. Okay, extended through the materials to form the 2D structure. Okay, 2D crystal structure. Is that okay? Okay, so how do we define the 7 crystal system? The lattice parameters and the interaction angles are used to classify unit cell. Okay, once the unit cell is um, the unit cells are identified, and we can define the crystal system. Okay, we can define a crystal system. Give you some example. For example, the crystal system is a cubic, and its actual relation is it's called the lattice parameters. Okay, lattice parameters. Okay, it's the actual length. Okay, and for the cubic system, its actual length are equal, right? Are equal, and the angles are rectangular, right? Okay, basically just a geometric game, right? It's just a geometric issues. For the hexagonal, A equals to B is now equal to C, and the alpha equals to beta equals to 90 degrees, and gamma equals to 120 degrees. Okay, it's called the hexagonal structure. Therefore, you can go through this slides. It will tell us how those 7 crystal systems related to the geometric parameters. Okay, so we can just look at it. And we have to define the number of atoms per unit cell. Right? We already mentioned the unit cell can extend through whole materials. Right? For example, here for the atoms right here. For example, we have 2 unit cells, 1 and 2, and this atom is divided by 2. It's a shear with two unit cell. Okay, therefore, half of this atom belongs to unit cell 1, and half of this atoms belongs to unit cell 2. Also, if there's an atom here, and it's in center of 8 unit cells. Okay, and the fraction of this atom is 1/8 in each unit cell. Okay, it's 1/8 in each unit cell. Okay, well, it's just a geometric game, right? It's not big deal. Okay, let's look at the first metal structure. It's called FCC. It's body center cubic. Body center cubic. It defines that with the each atom are located at the 8 corners, and there's 1 atom located center. Okay, therefore we call it body center. Okay, and basically there are 2 types of the structure presenting. If you want to present the atomic or the atomic structure, I have 2 different ways. The first is like figure A. It's a solid sphere. Okay, it's a solid sphere. And figure B shows the lattice and the basis. Okay, lattice and basis. It doesn't matter. It's the same thing. It just it's created. It's defined by the scientist. And for the second structure is called hexagonal close pack (HCP). Okay, it's called HCP. Okay, and this plan, we call it Basel plan. Okay, we call it Basel plan. Okay, the one of the famous materials with this structure is called graphite. Okay, it's a graphite, and the single atom thick of Basel plan in graphite is called graphene, right? It's called graphene. Okay, it's a graphene. Okay, it's called graphene. Okay, and the third one, a metal structure, it's called FCC. Okay, face center cubic. Okay, face center cubic. In each, that's mean in each face is the face, right? It's the face right here. It's the face right here, and there's a one atom in the center, right? It should be half atoms, and we have the other atoms at the corner, right here and here. Okay, it's called the face center cubic. It's called the face center cubic. Okay, give you guys a review that for the HCP structure, what's the bonding between these two atoms? And this bonding is bonding 1 and it's bonding 2. Which one is stronger? Which one is stronger? For example, we have a graphite structure. Of a graphite structure, the structure is like this HCP structure. Well, not, no, wow, it's a HCP structure. And for the bonding 1 and bonding 2, which one is stronger? Of course, the bonding 1 is stronger than bonding 2 because it's a covalent bond, right? And for the bonding 2, it's what? It's a secondary bond. Okay, it's a secondary bond. Okay, therefore the bonding 1 is much stronger than bonding 2. That's the reason why the graphite is easy to be peeled off. It's easy to be exfoliate, right? Okay, so let's look at the interaction with within the unit cell. Okay, we have to define a close packed direction. What's the close packed direction? The atoms are in continuous contact. Okay, continuous contact. And we can find a relation between the lattice parameter A0 and which relates the dimension of each unit cell. Okay, dimension of unit cell, which is related to the size of each atoms. Okay, so here we are discussing about the cubic structure. Okay, we always know, no matter it's a simple cubic, a body center cubic, face center cubic, it's all belong to cubic system, cubic structure. Okay, remember that we're discussing the cubic system. Therefore, the lattice parameter is A0. And A0 is related to the atomic radius, right? That is the size of the atoms, right? For example, we look at the simple cubic. Okay, simple cubic, and these two atoms are contact, right, with each other, right? And here, this distance is lattice parameter, and therefore the lattice parameter is equals to what? 2 times atomic radius, right? Atomic radius. And for the body center, which direction is the highest, is the close pack direction? It's the close pack direction. The direction existed the highest number of atoms. Here, right? Let's draw it. 1, 2, 3. Right, from this corner to okay, path through the body center to the other corner. Right. Therefore, we can figure out the relation between lattice parameter and atomic radius from this triangle, this, okay, and here is 90 degrees. Right? Therefore, we can find the relation between the lattice parameter corresponding to the atomic radius. And for the phase center, which direction is with the highest number of atoms? Here, right? From this corner to this corner and pass through the phase center. Okay, therefore we can use this triangle to find out the relation between the lattice parameter and the atomic radius. Okay, for atomic radius. Is that okay? Okay, next, there's some terminology. We have to define it. First is called the coordination number. It is the number of atoms touching a given atom or the number of its nearest neighborhood. Its nearest neighborhood. It's near, remember this, its nearest neighborhood. Okay. For example, for the symbol cubic, in this case, you can think of it, the atom here, how many coordination number of the atom here? Just think of it. And what is the coordination number of the atom here for BCC? Right? You can think of it. The nearest should be 8. 1, 2, 3, 4, 5, 6, 7, 8. For the atom here, I think 1, 2, 3, 4, 5, 6, 7, 8 nearest numbers. Okay. So it's called coordination numbers. And next is called the packing vector. What is packing vector? That is the fraction of space occupied by atoms, okay, modeled by a sphere, hot sphere, within a unit cell. Okay, for example, how many atoms in a single unit cell? So it can be calculated by this, the number of the number of atoms divided by cells times the volume of each atom divided by volume of unit cell. Okay. Therefore, it's dependent of the radius of the atoms. Okay, as long as all atoms have a fixed radius in a cubic box. Okay, cubic box. And it also related to what? It's also related to what? So higher packing vector means what? Means the higher density, right? Okay, means the higher density. Therefore, the theoretical density can be defined by the number of atoms per per unit cell times atomic mass divided by volume of unit cell times Avogadro's number. Okay, it's the for the pure element, pure materials. Okay, but for the composite or for some alloys, we have to measure it. Okay, okay. Okay, for the HCP structure, it's unicell. It's unicell. Okay. Okay. However, we can just look at the 1/3 of its structure, like this. 1/3 of its structure. Therefore, we can calculate the volume, right? Calculate the volume and divide it by. We can calculate the volume and calculate the number of atoms divided by the volume. We can find the packing vector. We can find the packing vector. Okay. Okay, there are some tables shows. Okay, for the simple cubic structure, what is coordination number? What is BCC structure? What is its coordination number? And what is the for the FCC structure? What is the coordination number? Okay, and we can find out the lattice parameter related to its atomic radius. And also you can see for the higher parking, for the higher vector of packing shows the higher density. Therefore, the element has the packing vector 0.74, like the copper, platinum, nickel has the higher density than that of the iron, and so on. Okay, and so on. Okay. So next, what is the allotropic or polymorphic transformation? Materials with more than one crystal structure are called the allotropic. It is pure elements. It's pure elements. Okay, it's pure element. The pure element has one more crystal structure. Okay. Okay. Or for the compound, it's called the polymorphic. Okay, for compound has more than one crystal structure, it's called polymorphic. Okay, polymorphic. For example, like iron has the FCC structure, but it changed to FCC at higher temperature. Okay, I will introduce this later in the chapter of phase diagram. Okay, phase diagram, phase transformation, and also like many ceramic materials such as silica or zirconium are polymorphic, and the crystal structures changes upon heating and doping. Okay. Okay, next, how do we define the crystal direction or crystal plan? Okay, I'll introduce how to define the crystal direction first. Okay, and the Miller indices are used to determine the crystal structure, the crystal direction and plan. Okay, and this is its step. Don't ask me why, it's just define. We can define the direction, we can define the crystal plan by the Miller indices. Just follow the steps. Okay, basically it's just the concept of vectors, right? Concept of vectors. Okay, it's not difficult, just vectors. Okay, for example, let's calculate the okay, let's calculate the vector from the origin here. if it is the unit cell, if it is a unit cell. First, the vector repositioned to pass through the origin. Okay, so this vector passed through the origin. It's no problem. And read off the projections in terms of unit cell dimension A, B, and C. For example, its intersection is here, right here, and for the Z is here, right? And for the cubic system, therefore we can figure out, okay, so it's A, X direction, and Y, and Z is A, B, C for lattice lattice parameters. Okay, it's a projection. It's a projection. Dimensional, it's a projection in terms of a unit cell dimension A, B, and C. Okay, therefore we can find out the intercept with the three axes, 1, 0, and half. So what's the 0 means? The 0 means the vector is what? There's no any projection, right? No projection on that dimension, okay, on that dimension. So therefore, we read out the projection 1, 0, and half, right? And then we adjust to the smallest integer volume. It's 2, 0, 1, and we use the square brackets, right? Therefore, we can define the blue vectors. Use the Miller indices. Okay, use the Miller indices. Also, just do the other practice. Shows the red vectors, right? And we can find out its a projection here, right? Projection here, right? Projection here and projection here. Therefore, we can find out its projection in terms of the unit cell dimension A, B, C is -1, 1, 1, and we put its minus the minus size. Use the overbar to represent it. Okay, therefore we use this Miller indices to define the vector. Okay, to define the vector. Okay, so it must be easy. For example, for the A, for the A, if we use the Miller indices, it's what? It's 1, 0, 0, right? For the B, what? It's 1, 1, 1, right? For the C, from this point to this point. Okay. Therefore, we can find out the direction C if we use the Miller indices to represent direction C is 1 bar, 2 bar, and 2. Is that okay? We use the 0 to 0 minus half, right? And 0 minus 1, and the 1 minus 0, right? Therefore, we can get the minus 1 half and minus 1 and 1, right? Adjust to a smallest integer is minus 2. Sorry, it's minus 1, minus 2, and 2. Right, and overbar, use the overbar to represent the minus size, 1 bar, 2 bar, 2. Right, therefore we get this. Okay. Okay, it's not difficult. It's just the vector. Okay, E just vector. Okay, several points should be noted about Miller indices. Okay, a direction and its negative. Direction and its negative are not equal. Are not equal. Therefore, 111 and 1 bar 11 are not equal. And the direction and its multiple are identical. Therefore, 111, 100, 200, and 300 are identical. And certain groups of direction are equivalent. Some properties in a cubic materials, we use the, we can define the 111 direction, family direction. For 12 direction in a cubic system belongs to 111 family. Okay, 111 family. Also, I'll introduce the crystal plan. You also have the family plan for crystal structure. Okay, for crystal structure. Okay, for crystal structure. Okay. Okay, so the other way to represent the direction, the crystal direction, is called repeat distance. What is repeat distance? That's the distance between lattice points along the direction. In the contact direction, the contact, it should be the direction between two atoms are contact. Okay, for example, here, this is the repeating distance. This distance is repeating distance because there's an atom and atom, and their contact, and this is the repeating distance. Okay, so we can repeat it here, repeating here, and repeating here. Also, here's the repeating distance, right? Okay, repeat here. Repeat here and here. Keep repeating. Is that okay? And the repeating distance. This is a FCC structure, right? Face center cubic. Therefore, its repeating distance equals to half times square 2 times lattice parameter A naught. A naught is here. Okay, okay. And the linear density is the reciprocal of repeat distance. Okay, it's the reciprocal of the repeated distance. Okay, and the packing fraction equals the linear density times 2 times atomic radius. And atomic radius, you can find it out from your periodic table, okay, or some, it's not difficult. You can find it. So okay, some definition of a repeat distance and linear density and the packing fraction. Okay, packing fraction. So, for example, for the 110 direction in FCC copper, what is packing fraction? Sorry, this is the wrong typo. It should be fraction. It should be fraction. You can figure it out its linear density, right? Because we know the direction is 110, and we know its crystal structure is FCC, and we know the copper. Therefore, we can find out the copper's atomic radius right here, right? So it's not difficult to find the copper's packing fraction in 110 direction. Okay. Okay, so maybe I'll stop the course here, and next I'm gonna introduce you the HCP structure, and because it's quite different from the cubic system, right? Because it consists of the basal plan. It's a hexagonal close packed structure, and the Miller indices define its direction is a little bit different from the cubic system. Okay, it's quite different from its cubic system. Maybe I'll introduce you this next time.